go ahead and find that comfortable position now. Let your shoulders drop away from your ears, let your hands fall open, and allow your body to sink just a little deeper into wherever you happen to be resting. There is nothing you need to do right now, nowhere you need to be, no problem that requires your attention in this moment. Tonight, we are going to take a journey together, not a demanding journey, not one that asks anything difficult of you at all. This is the kind of journey where you just let the words wash over you like warm water, carrying images and ideas into the gentle depths of your mind as you drift toward sleep. We are going to talk about something that scientists deep underground, in one of the most extraordinary places on Earth, have been quietly working on for decades. We are going to talk about the very nature of reality itself, about the invisible rules that govern every atom in your body, every star in the sky, every particle of light that has ever touched your skin. And we are going to talk about a crack, a tiny, whispering, tantalizing crack that has appeared in what we thought was a perfect and complete picture of existence. A crack that some physicists believe could lead us somewhere entirely new, to a deeper truth about what this universe actually is, and why it exists the way it does. But before we go any further, if you are enjoying this kind of content, science that wraps itself gently around you as you rest, stories about the cosmos that soothe rather than startle, please consider hitting the like button and subscribing to the Science Pillow. It helps this channel find its way to more curious, restful minds like yours, and it means I can keep making these journeys for you. Every subscription is genuinely appreciated. Now, settle in, close your eyes if you like, and let us begin. A crack in the foundation. Somewhere beneath the rolling green countryside on the border between France and Switzerland, where the Alps rise in the distance and the air carries the clean scent of mountain meadows, there exists one of the most extraordinary places ever built by human hands. It sits 100 meters underground, invisible from the surface, occupying a circular tunnel that stretches 27 kilometers in circumference, large enough, if you unrolled it, to stretch across an entire city. Inside this tunnel, in a vacuum colder than the emptiness between the stars, particles smaller than anything you could ever hope to see are traveling at very nearly the speed of light. They whip around and around this great underground ring hundreds of thousands of times every single second, and then, at carefully chosen moments, they are steered toward each other, and they collide. And in the blinding flash of that collision, for the tiniest sliver of a moment, conditions are recreated that existed only a fraction of a second after the universe was born. This is CERN, the European Organization for Nuclear Research, and for decades it has been the place where humanity goes to ask the deepest questions it knows how to ask. What is matter made of? How do forces work? Why does anything exist at all? The scientists here are not searching for practical applications, not looking to build a better engine or a faster computer. They are searching, with extraordinary patience and precision, for the truth about what reality is made of at its most fundamental level. And for a long time, for most of the 20th century and well into the 21st, they had a map. A beautiful, elegant, remarkably successful map of reality called the Standard Model of Particle Physics. This map described every fundamental particle ever discovered, explained how forces between them worked, predicted the outcomes of experiments with breathtaking accuracy. It was, and remains, one of the greatest intellectual achievements in human history. Scientists have called it the triumph of modern physics. Some have called it close to perfect. A few have quietly worried that it might be too perfect, that if it never broke down, never showed a flaw, physicists might never find the path beyond it. Then, in the data from CERN's experiments, something began to appear. Not all at once, not dramatically, not in a single blinding moment of revelation. It appeared the way a crack appears in a very old wall. Gradually, almost imperceptibly, a hairline fracture in the smooth surface of certainty. A measurement came back slightly different from what the standard model predicted. Then another measurement, slightly different in a related way. Then another experiment, at a different facility, seeing a related anomaly. And each time, the scientists looked at their instruments, checked their calculations, reanalyzed their data, and found that the measurement was real. The instruments were not malfunctioning. The math was not wrong. The universe was simply not behaving quite the way the theory said it should. This is what physicists mean when they talk about a crack in the standard model. Not a catastrophic failure. Not a dramatic collapse. A whisper from the data that says, there is something here you have not yet accounted for. There is a door in this wall, and beyond it lies territory your map has not yet drawn. The crack in the standard model is not cause for alarm. It is cause for wonder. It is one of the most exciting things that can happen in science. It means the universe has more to say than we have yet managed to hear. In this story, we are going to explore all of it. How the standard model was built, what it tells us, where it has broken down, and what might lie waiting for us on the other side of that crack. We will take our time with it. There is no rush. Let the science settle around you like snowfall, quietly and completely, as you rest, the machine at the edge of knowledge. What CERN actually is. To understand what CERN has found, you first need to understand what CERN actually is and what it does. Because the Large Hadron Collider, the machine at CERN's heart, is not simply a large scientific instrument the way a telescope or a microscope is a scientific instrument. It is something altogether more extraordinary than that. It is, in a meaningful sense, the most complex machine ever built by human civilization. Construction of the Large Hadron Collider began in 1998 and involved more than 10,000 scientists and engineers from over 100 countries. It was assembled in the same tunnel that had previously housed an earlier, smaller particle accelerator called the Large Electron Positron Collider, or LEP. That tunnel itself was an engineering marvel when it was constructed in the 1980s. A precisely circular tube bored through the limestone bedrock beneath the Franco-Swiss border, sitting 100 meters underground to protect it from cosmic radiation and surface disturbances. When the LHC was installed, that tunnel became something else entirely. At its core, the Large Hadron Collider is a machine for accelerating protons, the positively charged particles found in the nuclei of every atom, to velocities so close to the speed of light that the difference becomes almost philosophical. At full power, protons inside the LHC travel at 99.9999991% of the speed of light. To put that another way, if you and a beam of light started a race around the LHC's 27-kilometer track at exactly the same moment, the light would be only 9 meters ahead of the proton beam after one full lap. At that speed, each proton completes 11,245 circuits of the 27-kilometer ring every single second. Two beams of protons travel in opposite directions around the ring, guided by a system of superconducting electromagnets. 1,232 dipole magnets in total, each one the size of a small truck. Each one cooled to a temperature of minus 271 degrees Celsius. That is colder than the average temperature of outer space, which sits at around minus 270 degrees. Inside the LHC, it is quite literally colder than the void between the stars. This extreme cold is necessary because at those temperatures, certain metals become superconducting. They carry electrical current with zero resistance, allowing the magnets to generate the powerful fields needed to bend the proton beams around the ring without any energy loss. The vacuum inside the beam pipes is equally extreme. Scientists describe it as an ultra-high vacuum, a cavity as empty as interplanetary space. The internal pressure is 10 times less than the pressure on the surface of the Moon. Even a single molecule of ordinary air inside the beam pipe could cause a proton to veer off course or collide with something it should not, ruining an experiment. When conditions are right, the two beams, each traveling in its own pipe, curving around the ring in opposite directions, are steered toward each other at 4 specific points around the track. At each of these collision points, the beams cross and the protons within them have a chance to collide. Around 600 million collisions take place every single second. Each collision releases an enormous burst of energy and creates a cascade of new particles, most of them extraordinarily short-lived, vanishing in fractions of a second and leaving trails of data in the vast detectors that surround each collision point. Those detectors are themselves extraordinary structures. The largest, called Atlas, is 45 meters long, 25 meters tall, and weighs 7,000 tons. It is built like a great cylindrical onion, layer upon layer of sensitive instruments, each designed to capture and measure different kinds of particles emerging from the collisions at its center. The second general-purpose detector, CMS, the compact muon solenoid, is smaller but even heavier, weighing around 14,000 tons, containing a superconducting solenoid magnet that generates a field 100,000 times stronger than the Earth's magnetic field. These machines take images of each collision 40 million times per second, capturing data at a rate that would overwhelm any conventional storage system. Sophisticated software filters this torrent of data in real time, identifying the most interesting collisions and discarding the rest. What are the scientists looking for in all of this? They are looking for the fundamental building blocks of matter and the forces between them. They are recreating, for tiny fractions of a second, the conditions that existed in the universe when it was only a fraction of a second old, and so hot and dense that matter itself had not yet condensed into the forms we recognize today. They are watching the birth of particles that normally do not exist in our cool, quiet universe. Particles that wink into and out of existence too briefly to be measured by anything other than the most sensitive instruments ever constructed. And they are comparing what they see to the predictions of their most powerful theory of nature, the Standard Model of Particle Physics. CERN is also more than one experiment. In addition to the giant Atlas and CMS detectors, the LHC hosts several more specialized instruments. The LHCb detector, the Large Hadron Collider Beauty Experiment, is specifically designed to study particles called beauty quarks, or B-quarks, and the slight differences between how matter and antimatter behave. It was in data from LHCb that some of the most intriguing hints of new physics first appeared. The ALICE detector is built to study heavy ion collisions. Collisions between lead nuclei rather than protons, recreating the extreme conditions of the early universe in a different way, studying a state of matter called a quark-gluon plasma, where quarks are no longer confined within protons and neutrons but flow freely in a kind of primordial soup. And the NA62 experiment, not in the main LHC ring but nearby at the CERN North area, is built to study an entirely different category of particles called kaons, in extraordinary quantities and with extraordinary precision. The whole enterprise costs CERN roughly 1.3 terawatt-hours of electricity per year, the same as the entire electrical consumption of the Canton of Geneva. It employs thousands of scientists and staff from more than 20 member states, with contributions from many more countries around the world. It is a monument to what human beings can accomplish when they set aside national boundaries and competitive interest and simply pursue the truth together. And what CERN has been pursuing with ever greater determination and precision is the answer to a question that keeps physicists up at night. Is the Standard Model the final word on reality, or is there something beyond it? Our best map of everything. The Standard Model. To understand why the cracks in the Standard Model matter so much, you need to appreciate just how extraordinary the Standard Model is in the first place. This is not a theory that has been found wanting because it is inadequate or incomplete in obvious ways. This is a theory that has been tested more rigorously and found more accurate than almost any scientific theory in history. Understanding why physicists both love it and are desperate to find its limits requires spending a little time with what the Standard Model actually says. The Standard Model of particle physics is, at its heart, an answer to a question that human beings have been asking for at least 2,500 years. What is everything made of? The ancient Greeks proposed that matter was made of indivisible units they called atoms. It took until the late 19th century for science to confirm that atoms really do exist, and another few decades to discover that atoms themselves have inner structure, a dense nucleus surrounded by electrons. Then the nucleus was found to be made of protons and neutrons, and those particles were themselves found to be made of still smaller things called quarks. The Standard Model is the culmination of all that peeling away, the deepest layer of the onion that science has been able to reach. According to the Standard Model, all matter is built from two types of fundamental particles, quarks and leptons. There are 6 varieties of quark, known by the whimsical names that physicists gave them: up, down, charm, strange, top, and bottom. They come in 3 pairs, or generations. The up and down quarks are the lightest and most common, and they are what protons and neutrons are made of. A proton consists of 2 up quarks and 1 down quark, while a neutron consists of 2 down quarks and 1 up quark. The other 4 quarks are heavier, less stable versions that are produced in high-energy collisions, but quickly decay into lighter forms. Quarks are never found alone in nature. They are always bound together by an extraordinarily powerful force, confined within composite particles called hadrons. The force that binds them is so strong that trying to pull a quark out of a proton would require more energy than it takes to create an entirely new pair of quarks. So, nature always responds to such an attempt by producing new particles rather than allowing an isolated quark to exist. This behavior, called color confinement, is one of the most unusual and fascinating features of the subatomic world. The leptons form their own family of 6: the electron, the muon, the tau, and three varieties of neutrino: the electron neutrino, the muon neutrino, and the tau neutrino. Unlike quarks, leptons are not subject to the strong nuclear force and can exist on their own. The electron is the most familiar of these. It is the particle that orbits atomic nuclei and makes chemistry possible. The muon is essentially a heavier version of the electron, about 200 times more massive, with the same electric charge but a much shorter lifetime. The tau is heavier still. The three neutrinos are extraordinarily light, carry no electric charge, and interact so weakly with other matter that a neutrino produced in the heart of the Sun can pass through the entire Earth as though it were not there. Trillions of neutrinos from the Sun are passing through your body every second as you rest, and not one of them has any effect on you whatsoever. Then there are the bosons, the particles that carry forces between the matter particles. The photon carries the electromagnetic force. The gluon carries the strong nuclear force that binds quarks together, and the W and Z bosons carry the weak nuclear force responsible for certain types of radioactive decay. These force-carrying particles are the messengers of interaction. When two electrons repel each other, they do so by exchanging photons. When a quark changes its identity during radioactive decay, it does so via the exchange of a W boson. And then, completing the picture, there is the Higgs boson, the particle that gives all the other particles their mass. The Higgs boson was the last piece of the Standard Model to be confirmed, discovered at CERN in 2012 after a search that had lasted nearly half a century. When physicists announced its discovery, there were tears in the audience. Peter Higgs, the British physicist who had theorized its existence back in 1964, was in the room, and he wept. It was one of the most celebrated moments in the history of science. The final confirmation that this extraordinary theoretical framework was a complete and accurate description of the particle world. In total, the Standard Model describes 17 fundamental particles. All the atoms in your body, all the light that reaches your eyes, all the forces that hold matter together and make chemistry and biology possible. All of it arises from the interactions of these 17 particles. The Standard Model also successfully unifies three of the four known fundamental forces of nature: electromagnetism, the strong nuclear force, and the weak nuclear force. It does not include gravity, which remains stubbornly outside its framework. And despite its extraordinary success, physicists have always known it was incomplete. Not because it gets anything wrong, but because it says nothing about gravity, says nothing about dark matter or dark energy, and leaves many deep questions unanswered. The discovery of the Higgs boson was, paradoxically, both a triumph and a challenge. It confirmed the model, but it also left the physicists with nowhere left to hide. If the universe contained only what the Standard Model described, there was no new territory left to explore within its borders. The only hope was that some experiment would reveal a deviation, a number slightly off, an anomaly that could not be explained by the existing theory, a crack in the perfect wall. The word quark, incidentally, has a delightful origin story. It was coined by physicist Murray Gell-Mann in 1964, and he took it from a line in James Joyce's novel Finnegan's Wake, 3 quarks for muster mark. At the time, only 3 types of quark were known, so the reference felt apt. Even deep physics, it seems, cannot entirely escape the poetry of language, the discovery that changed everything: Kaons, anomalies, and the 50% excess. let us drift now toward the discovery itself, the one that has most recently and most compellingly suggested that the standard model has an edge, a boundary beyond which something new lies waiting. To understand it, you need to know about a particle called a kaon. A kaon is a type of particle called a meson, a composite particle made of one quark and one antiquark. Specifically, a positively charged kaon consists of an up quark and an anti-strange quark bound together. Kaons are not common in everyday life. They exist only in high-energy environments like cosmic ray showers and particle accelerators. But they have a long history in physics as sensitive probes of the fundamental forces. In the 1950s and 1960s, studying kaons led directly to some of the most important discoveries in particle physics, including the first evidence that nature treats matter and antimatter slightly differently, a violation of what physicists call CP symmetry. The Nobel Prize in Physics was awarded in 1980 for that discovery. Now, more than 6 decades later, kaons have delivered another potentially revolutionary message from the subatomic world. This time, the message came from an experiment at CERN called NA62, an experiment built in the CERN North area specifically to study a single, extraordinarily rare process: the decay of a charged kaon into a charged pion and a pair of neutrinos. Consider for a moment just how rare this process is. The standard model of particle physics predicts, with great precision, that fewer than 1 in every 10 billion charged kaons will undergo this specific type of decay. 1 in 10 billion. If you had a stadium holding 70,000 people, and every single person in that stadium represented a kaon, you would need nearly 143,000 such stadiums, every seat filled, before you would statistically expect to see this decay happen even once. It is, by any measure, a vanishingly rare occurrence. And yet it is precisely this rarity that makes it so scientifically valuable, because such rare processes are extraordinarily sensitive to tiny influences from particles or forces that the standard model does not know about. If there is some new, as yet undiscovered particle lurking in the quantum vacuum, gently influencing the behavior of kaons, this ultra-rare decay rate is one of the places where that influence is most likely to show up as a measurable deviation. The NA62 experiment was built over more than a decade with precisely this in mind. It is roughly 270 meters long, housed in 2 caverns in the CERN North area. A high-intensity proton beam from CERN's superproton synchrotron, itself a massive accelerator, slams into a stationary target, producing a torrent of nearly 1 billion secondary particles every second. About 6% of those particles are charged, kaons. The NA62 detector tracks each kaon with extraordinary precision, identifying all of its decay products except the 2 neutrinos, which cannot be detected directly and instead manifest as missing energy in the measurement. Finding the 1 in 10 billion signal in all of that data is, as one physicist put it, like looking for a needle in a haystack. But first, you have to build the haystack. The collaboration collected data between 2016 and 2022, with a significant improvement after detector upgrades completed in 2021, allowed the experiment to operate at 30% higher beam intensity and collect signal candidates 50% faster than before. The analysis required meticulous work to distinguish genuine signal events from all the background processes that could mimic them. 9,999,999,999 other decays for everyone they were looking for. On September 24, 2024, the NA62 collaboration presented its results at a seminar at CERN. The announcement was the first-ever experimental observation of this ultra-rare decay at the 5 sigma level of statistical significance, the threshold traditionally required in particle physics to declare a genuine discovery rather than a statistical fluctuation. The measured decay rate was approximately 13 occurrences per 100 billion kaons. That result carries a 25% relative uncertainty, which is the most precise measurement of this process ever achieved. And here is where the story becomes genuinely tantalizing. The measured rate is about 50% larger than the standard model's prediction. 50% larger. The standard model predicts roughly 8.6 events per 100 billion kaons. The measurement found 13. That is a significant excess, not enough, given the current measurement uncertainties, to claim definitive proof of new physics, but enough to be scientifically striking. Enough to be, as physicists say, intriguing. The result is compatible with the standard model at roughly the 2 sigma level when uncertainties are properly accounted for, which means it could still be explained by statistical fluctuation. But it could also be a genuine signal that some particle or force not included in the standard model is secretly participating in this rare decay, nudging the rate upward. The NA62 collaboration was careful and measured in its language. Searching for hints of new physics in this decay requires more data, but this result is a leap forward, said Karim Masri, the NA62 physics coordinator from Lancaster University. The experiment is continuing to collect data, and within the next few years, the collaboration expects to have enough information to either confirm the excess as genuine new physics or determine that it is within the statistical noise of the standard model prediction. The world of particle physics is watching very carefully. What makes this particular result so exciting is not just the numbers themselves, but the context. The kaon decay measurement does not exist in isolation. It is part of a pattern, a constellation of measurements from multiple experiments over many years, all nudging in a similar direction. All suggesting that the standard model, however successful, may not be telling the complete story of what happens when particles decay and transform. What cracks in physics actually mean. A history of anomalies. Before we explore what might lie beyond the standard model, it is worth taking a moment to appreciate what a scientific anomaly actually means, and why this particular pattern of anomalies is so significant. The history of physics is, in many ways, a history of anomalies, tiny, puzzling discrepancies that eventually, when taken seriously and investigated with enough patience, opened the door to entirely new understanding of nature. In the late 19th century, the orbits of the planets in our solar system were considered to be understood. Newton's law of gravitation described them beautifully, except for Mercury. The orbit of Mercury precessed, meaning that the point of its closest approach to the Sun slowly rotated over time, and it did so a little faster than Newtonian mechanics predicted. The discrepancy was tiny, about 43 arcseconds per century. For decades, astronomers tried to explain it away by invoking an undiscovered planet or errors in measurement, or small inaccuracies in calculations. But in 1915, when Albert Einstein developed his general theory of relativity, one of the first things he did was calculate Mercury's orbital precession. His new theory predicted exactly the observed value. The anomaly had been telling the truth all along. It was not an error in measurement. It was a signal that Newton's theory of gravity was incomplete. The pattern has repeated itself throughout the history of physics. Anomalies that looked like noise eventually revealed new physics. The discovery of neutrino oscillations came from unexpected deficits in neutrino counts from the Sun. The discovery of cosmic acceleration came from measurements of distant supernovae that did not dim at quite the expected rate. In each case, the anomaly was not a mistake. It was the universe whispering, "Look here, there is more than you know." The Standard Model has accumulated a number of such whispers over the past decade, and the Na62 kaon result is only the most recent and perhaps the clearest. The LHCb experiment at CERN has spent years studying particles called B mesons, heavier relatives of kaons, and how they decay. For a period between 2019 and 2021, measurements from LHCb suggested that B mesons were decaying into electrons more often than into muons, when the Standard Model predicts both processes should happen at essentially identical rates. This potential violation of what physicists call lepton flavor universality was reported with a significance of 3.1 sigma. Tantalizingly suggestive, but not enough for a discovery claim. Subsequent reanalysis with more data reduced the significance of that particular anomaly, suggesting it may have been a statistical fluctuation, but the LHCb experiment continues to probe this territory. Also, in 2025, the LHCb collaboration announced another significant result: the first ever observation of matter-antimatter asymmetry, a phenomenon called CP violation, in the decay of baryon particles. Baryons are particles made of 3 quarks, including the protons and neutrons that make up atomic nuclei. CP violation had previously been observed in mesons, but never in baryons. The new measurement found that baryons called lambda B particles decay into specific sets of lighter particles about 5% more often than their antimatter counterparts. The antibaryons decay into the equivalent final state. While this observation is consistent with the Standard Model, it represents a new window into one of the deepest puzzles in all of physics: why the universe is made of matter and not antimatter. There are also hints from outside CERN. For several years, measurements at Fermilab in the United States suggested that the W boson, one of the force-carrying particles of the weak nuclear force, might be slightly heavier than the Standard Model predicts. This result, if confirmed, would represent a clear departure from the Standard Model's predictions, since the masses of the W and Z bosons are among the theory's most precisely predicted quantities. The scientific community is still working to reconcile measurements from different experiments and understand whether the discrepancy represents genuine new physics or systematic errors in the measurements. And then there is the muon anomalous magnetic moment, known among physicists as the muon G-2 problem. The muon has a magnetic moment, a property related to how it behaves in a magnetic field, and the Standard Model predicts its value with extraordinary precision. Measurements from an experiment at Fermilab have consistently found a value slightly higher than predicted. A discrepancy that has persisted across multiple rounds of data collection and analysis. The most recent results maintain a tension with the Standard Model at around the 3 to 4 sigma level, keeping this anomaly firmly in the category of something to watch very carefully. None of these individual anomalies, taken in isolation, constitutes proof of physics beyond the Standard Model. Physicists require 5 sigma, a 1 in a few million chance of a statistical fluke, before declaring a discovery, and most of these hints sit below that threshold. But the pattern is what concerns and excites physicists most. Multiple experiments, multiple types of measurements, multiple particles, all showing hints of behavior that the standard model did not quite predict. The whispers are growing louder. The cracks in the wall are accumulating, and the question becomes not just whether there is new physics to be found, but what form that new physics might take. The mystery of what hides in the dark. Dark matter and dark energy. To understand why finding physics beyond the standard model is so urgently necessary, you need to appreciate just how much of the universe the standard model simply does not describe. This is perhaps the most humbling fact in modern science, and it is one that physicists have had to come to terms with over the past few decades. Everything the standard model accounts for, all the particles and forces it describes, every atom and photon and quark and lepton that makes up what we can see and touch and measure, constitutes only about 5% of the total matter and energy content of the universe. The rest is invisible, literally invisible. It does not absorb, reflect, or emit light of any kind. It does not interact with the electromagnetic force at all, which means no detector built to measure electromagnetic phenomena can directly sense it. We know it is there only because of its gravitational effects on the things we can see. And yet it makes up the vast majority of everything. The first component of this invisible cosmos is dark matter, a mysterious substance that constitutes approximately 27% of the universe's total mass energy content. The evidence for its existence is overwhelming. Stars at the edges of spiral galaxies orbit their galactic centers far too fast to be held in their orbits by the gravity of the visible matter alone. They should have flung themselves out into intergalactic space long ago. The only way to explain their stable orbits is to postulate vast halos of unseen matter surrounding each galaxy, providing the extra gravitational pull needed to keep the stars in place. Galaxy clusters bend light from objects behind them to a far greater degree than their visible matter alone could account for, a phenomenon called gravitational lensing that reveals the presence of enormous quantities of invisible mass. The large-scale structure of the universe, the way galaxies and galaxy clusters are distributed across cosmic space in great filaments and sheets, matches the predictions of models that include dark matter and does not match models that leave it out. We know dark matter exists. We simply have no idea what it is. It is not made of ordinary atoms. If it were, there would be visible stars and gas clouds that we are somehow missing, and precision cosmological measurements rule this out. The leading theoretical candidates are hypothetical particles that have never been directly detected, weakly interacting massive particles, or WIMPs, that would interact with ordinary matter only through gravity and the weak nuclear force. Axions, extraordinarily light particles, first proposed to solve a different problem in quantum chromodynamics. Or perhaps particles from an entirely separate sector of physics, a dark world of particles and forces that parallels our own but interacts with it only gravitationally. If dark, matter is made of particles, and most physicists think it probably is, then those particles are not in the standard model. They cannot be. The standard model has been tested with extraordinary thoroughness, and none of its known particles have the right properties to account for dark matter, which means that discovering dark matter necessarily means discovering physics beyond the standard model, a new particle or several new particles that science has not yet encountered. CERN has been searching for dark matter particles directly. If they are produced in proton-proton collisions at the LHC, they would pass through the detectors without interacting, leaving behind only their signature as missing energy, the amount of energy that appears unaccounted for after a collision. So far, no clear signal of direct dark matter production has been found. But the search continues, and each run of the LHC constrains the possible properties of dark matter particles more tightly, narrowing down the parameter space where they might hide. Even more mysterious than dark matter is dark energy, the name physicists give to whatever is causing the universe's expansion to accelerate. In 1998, two independent teams of astronomers studying distant supernovae discovered something that contradicted all expectations. Instead of slowing down over time under the influence of gravity, as everyone had assumed, the expansion of the universe is speeding up. Galaxies that are far from us are moving away not just fast, but faster than they used to be. The universe is not gently decelerating toward some eventual equilibrium or collapse. It is being pushed, as though by some kind of repulsive force operating throughout all of space, accelerating the expansion indefinitely. That mysterious pushing agent is dark energy, and it is even more prevalent than dark matter. It constitutes approximately 68% of the total energy content of the universe. If you were to take all the matter in the observable universe, every star, every planet, every nebula, every galaxy, every atom of hydrogen drifting through intergalactic space, and compare it to the total energy budget of the cosmos, that matter would represent less than 1/3 of what is accounted for by dark energy alone. The universe is overwhelmingly composed of something we do not understand at all. Dark energy has been compared to the cosmological constant, a mathematical term that Einstein added to his equations of general relativity and later called his greatest blunder, because he had introduced it to make the equations describe a static universe, and then discarded it when observations showed the universe was expanding. Ironically, the discovery of cosmic acceleration suggests something very like the cosmological constant might be real after all, an intrinsic energy of empty space that pervades the universe and acts as a kind of repulsive pressure. But this interpretation raises its own profound puzzles. Quantum field theory, the mathematical framework that underlies the Standard Model, predicts a value for the energy of empty space that is vastly larger than what observations of dark energy suggest, off by a factor that can be expressed roughly as 1 followed by 120 zeros. This is considered one of the worst predictive failures in all of theoretical physics, and no one has yet found a satisfying explanation for why the actual value is so incomprehensibly smaller than the predicted one. Together, dark matter and dark energy represent a kind of cosmic embarrassment for the Standard Model. A reminder that our best theory of the fundamental particles and forces describes only a tiny fraction of everything that exists. The other 95% remains, for now, a mystery. And any crack in the Standard Model, any measurement that deviates from its predictions, carries with it the hope that it might be our first glimpse of the physics that describes the invisible majority. The great antimatter puzzle. Why are we here? There is another mystery that the Standard Model cannot fully resolve, and it is perhaps the most existentially profound puzzle in all of physics. It is the mystery of why there is anything at all, why you exist, why the universe exists, why, after the Big Bang, matter remained instead of being annihilated. When the universe came into existence approximately 13.8 billion years ago, the prevailing understanding is that matter and antimatter were created in equal amounts. Every particle of matter produced in those first instants had a corresponding antiparticle. A particle with the same mass but opposite charge and other quantum properties reversed. When a particle and its antiparticle meet, they annihilate each other in a burst of pure energy. In the unimaginably hot and dense conditions of the early universe, matter and antimatter particles were constantly being created and annihilated, popping in and out of existence in a frenzied equilibrium. As the universe expanded and cooled, conditions reached a point where the creation of new particle-antiparticle pairs ceased, but the annihilation of existing ones continued. If perfect symmetry had been preserved, if matter and antimatter had truly been created in exactly equal numbers, all of it should have annihilated, leaving a universe consisting of nothing but radiation. No atoms, no molecules, no stars, no planets, no life. Nothing but light. And yet, here we are. The universe clearly did not annihilate itself. Instead, there was a tiny surplus of matter over antimatter, roughly one extra matter particle for every billion matter-antimatter pairs. That tiny surplus survived the great mutual annihilation, and it is all the matter in the observable universe today. Every atom in your body, every star in the night sky, every galaxy in the cosmos, all of it is the residue of that 1 in a billion excess that somehow tilted the scales toward matter in the first instance of existence. The Standard Model does include a mechanism for matter-antimatter asymmetry, a subtle violation of what physicists call CP symmetry, which means that the laws of physics are not perfectly identical when you simultaneously reverse all charges, C symmetry, and mirror all spatial directions, P symmetry. CP violation was first observed experimentally in 1964 in the decay of neutral kaons, and the discovery earned the Nobel Prize in Physics in 1980. CP violation has since been observed in other particles as well, and LHCb's 2025 observation of CP violation in baryon decays added baryons, the particles that make up most of the ordinary matter in the universe, to that list for the first time. But here is the problem. The amount of CP violation predicted and observed within the Standard Model is nowhere near large enough to explain the matter. Antimatter asymmetry we see in the universe. The Standard Model's CP violation is many orders of magnitude too small to account for why there is a universe rather than nothing. This tells physicists with certainty that there must be additional sources of CP violation beyond those described by the Standard Model. New physics, new particles, new interactions that provided the extra asymmetry needed for matter to win out over antimatter in the early universe. This is why the study of CP violation is one of the highest priorities at CERN and at other particle physics facilities around the world. Every new observation of matter-antimatter asymmetry, every new measurement of CP violation in any particle system adds another piece to the puzzle of how the universe managed to exist. And any deviation from the Standard Model's predictions, any hint that there is more CP violation than the model accounts for, is a potential clue to the physics that gave rise to everything. The antimatter mystery is, in the end, the deepest mystery of all. It is asking, why is there something rather than nothing? And the answer, if physics can find it, lies beyond the Standard Model. What lies beyond? The theories at the edge of knowledge. When physicists talk about what might lie beyond the Standard Model, they are not speculating idly. There are well-developed, mathematically sophisticated theoretical frameworks that extend the Standard Model in various directions, each addressing some of its known limitations and each making specific testable predictions about what experiments should find if the theory is correct. The most prominent of these is supersymmetry, often abbreviated as SUSY. Supersymmetry is, at its core, a proposed symmetry between two fundamentally different types of particles. In the Standard Model, particles come in two categories: fermions, which are the matter particles like quarks and electrons, and bosons, which are the force-carrying particles like photons and gluons. Fermions and bosons obey very different mathematical rules. They behave differently in groups. They cannot occupy the same quantum state in the same ways, and they seem to be fundamentally distinct kinds of entities. Supersymmetry proposes that they are not distinct at all, but are two sides of a single symmetry. Every fermion in the Standard Model, according to supersymmetry, has a corresponding boson partner called a sparticle, and every boson has a corresponding fermion partner. The electron has a selectron. The quark has a squark. The photon has a photino. None of these sparticles have been detected, but the theory predicts they must exist, just at higher masses than we have yet been able to produce. Supersymmetry is compelling for several reasons beyond aesthetic elegance. It provides a natural explanation for why the Higgs boson is as light as it is, a persistent puzzle called the hierarchy problem. It predicts that the three fundamental forces of the Standard Model merge into a single unified force at very high energies, something that is nearly achieved in the Standard Model but not quite, and that supersymmetry corrects. And, crucially, it provides a natural candidate for dark matter. The lightest supersymmetric particle, called the neutralino, would be stable, massive, and interact only weakly with ordinary matter, making it an excellent candidate for the dark matter particle that permeates the universe. The Large Hadron Collider was widely expected by many physicists to find evidence of supersymmetric particles. The energy scales at which the LHC operates were supposed, based on theoretical arguments, to be high enough to produce sparticles if they exist. But as the LHC has run through multiple phases and analyzed increasingly large datasets, no sparticles have appeared in the data. This has not killed supersymmetry. It has simply pushed the possible masses of sparticles higher to energy scales beyond the LHC's reach. The theory remains viable, just constrained. String theory is a more radical departure from the current framework. Rather than treating fundamental particles as mathematical points, as the Standard Model and quantum field theory do, string theory proposes that the most fundamental entities are not points, but tiny vibrating strings of energy. These strings are extraordinarily small, at least 20 orders of magnitude smaller than a proton. Their different vibrational patterns give rise to the different particles we observe, just as different modes of vibration of a physical string produce different musical notes. One of the vibrational modes of a string corresponds to the graviton, the hypothetical particle that would carry the force of gravity, which is why string theory naturally incorporates gravity in a way the Standard Model does not. String theory requires the universe to have more spatial dimensions than the three we observe, typically 10 or 11 in total, with the extra dimensions curled up on themselves into geometrical shapes so tiny that they are completely unobservable at current energy scales. The exact shape of these extra dimensions determines the physical properties of the particles and forces that emerge from string theory, and there is an almost unimaginably large number of possible shapes, each giving rise to a different version of physics. This vast landscape of possible universes is one of the most debated aspects of string theory. It may be that our universe is one of an enormous ensemble, with different physical constants in different regions, and we happen to find ourselves in one where the constants are compatible with the existence of complex structures and life. There are also theories of extra dimensions that do not require string theory. Proposals that gravity might leak into extra spatial dimensions and thus appear weaker than the other forces. The strong and weak nuclear forces and electromagnetism operate only in our 3 dimensions, and thus seem much more powerful than gravity at short distances. If extra dimensions exist at the scales probed by the LHC, microscopic black holes could be produced in proton-proton collisions, short-lived but detectable. None have been found so far, but their absence has helped scientists constrain the possible properties of extra dimensions. Loop quantum gravity is a third major approach to quantum gravity, quite different from string theory. Rather than treating space-time as a background arena in which particles and fields exist, loop quantum gravity proposes that space-time itself is quantized, that it is made of discrete, finite chunks rather than being a smooth continuum. At the Planck scale, which is approximately 10 to the minus 35 meters, space is not a seamless fabric but a network of interconnected loops and nodes, a kind of quantum geometry from which the smooth spacetime of everyday experience emerges only as an approximation at larger scales. Loop quantum gravity does not require extra dimensions and makes no predictions about supersymmetric particles, which gives it a more conservative, mathematical character than string theory. But it faces its own substantial challenges in making clear, testable predictions at energy scales that real experiments can actually reach. The frontier of quantum gravity remains largely untested territory. Grand unified theories, or GUTS, propose that the 3 forces described by the Standard Model are actually different manifestations of a single underlying force that was unified at the extraordinarily high temperatures of the very early universe. As the universe cooled, this unified force broke into the 3 we observe today, like water freezing into different crystal structures. GUTAs typically predict processes that have not yet been observed, such as proton decay, the spontaneous disintegration of a proton into lighter particles over extremely long timescales. No proton decay has ever been seen, but dedicated experiments around the world continue to look for it in enormous underground tanks of purified water or other materials, because its detection would be powerful evidence for this category of theory. The Super Kamiokande detector in Japan, deep underground beneath Mount Ikeno, has been watching for proton decay for decades, with every year of non-observation placing tighter and tighter constraints on the possible decay rates predicted by different GUT models. What all of these frameworks have in common is that they are attempts to go beyond the Standard Model, to extend our understanding of nature into territory the current theory cannot reach. Each one makes specific predictions, and each one waits to be tested by the next generation of experiments. The crack in the Standard Model that measurements like the Na62 kaon decay result suggest may exist is precisely the kind of signal that will help physicists determine which, if any, of these theories is on the right track. The deep philosophy. What it means if reality is different. Take a slow, easy breath now. Let your mind wander with this for a moment, because what we are talking about here is not just science in the narrow sense of measurement and calculation and laboratory work. What we are talking about, at its deepest level, is the nature of existence itself. What the Standard Model is, and what lies beyond it, is intimately connected to the most fundamental questions philosophy has ever asked. Why is there something rather than nothing? Why do the laws of physics have the form they do? Is there a deeper principle from which reality arises? When physicists discovered quantum mechanics in the early 20th century, it did not just add new knowledge to the existing picture of the world. It shattered the existing picture and replaced it with something stranger and more beautiful than anything anyone had imagined. It revealed that, at the smallest scales, reality does not work the way every day. Experience suggests particles do not have definite positions or velocities until they are measured. Light behaves as both a wave and a particle depending on how you look at it. Two particles can be correlated across vast distances in ways that have no classical explanation. The act of observation is woven into the fabric of the physical world in ways that continue to provoke philosophical debate a century after the theory was developed. If the cracks in the standard model lead to genuinely new physics, new particles, new forces, perhaps even new dimensions of space, the shift in our understanding of reality could be just as profound. Imagine discovering that the universe has 7 spatial dimensions rather than 3, with the extra 4 curled up so tightly that we have never noticed them. The implications would extend far beyond physics. The very concept of space, of distance, of here and there, would need to be reimagined. Imagine discovering the identity of dark matter, that the universe is permeated by a hitherto unknown type of particle, a whole new class of matter that interacts with our world only through gravity. We would need to revise everything we think we understand about the composition of the cosmos. The universe we thought we knew would turn out to be a thin veneer over a vast ocean of something else entirely. The atoms of our bodies, the matter of our world, would be revealed as the exception rather than the rule, a tiny minority of what actually exists. Imagine understanding, finally, why there is matter rather than antimatter. Understanding the mechanism that tilted the scales in matter's favor in the first fractions of a second after the Big Bang and allowed the universe to persist rather than annihilate itself. This would be an answer to the question of why anything exists at all, delivered not by philosophy or religion, but by measurement and mathematics. It would be one of the most extraordinary moments in the history of human thought. The physicist Richard Feynman, who contributed enormously to the development of quantum electrodynamics, the theory of how light and matter interact, once said that if you think you understand quantum mechanics, you don't understand quantum mechanics. He meant that the theory is so strange, so counterintuitive, so unlike anything that everyday experience prepares us for, that genuine understanding requires letting go of the comfortable assumptions of classical physics and sitting with the strangeness. The same might eventually be said of whatever comes next. Whatever lies beyond the standard model, it will almost certainly be stranger and more beautiful and more mind-bending than what we currently know. That is how physics has always worked. Each expansion of knowledge has revealed not just new answers, but new depths of mystery, new questions that could not even have been formulated before the discoveries that gave rise to them. There is something profoundly humbling and profoundly exhilarating about all of this. The universe is under no obligation to make sense to us. It does not owe us theories that are simple or comprehensible or intuitively satisfying. And yet, and this is perhaps the most remarkable fact of all, it has turned out to be the kind of place that can be understood. Mathematics, the language of pure abstract thought, has turned out to be the language of nature. The equations we write on whiteboards in universities and laboratories, the calculations we perform on computers, have been astonishingly accurate guides to the behavior of the physical world at every scale we have been able to probe. There is no obvious reason why this should be so. And yet it is. The universe is comprehensible. It rewards inquiry. It responds to questions with answers. Sometimes those answers are not quite right. Try again. But that, too, is a form of illumination. The future of CERN. What comes next? The story is not finished. In fact, in many ways, the most exciting chapters are still to come. The Large Hadron Collider itself is in the process of preparing for its most powerful configuration yet. And beyond the LHC, even grander machines are being planned that will push the frontiers of human knowledge into territory that, right now, we can only glimpse from a distance. The current era of LHC operation, Run 3, has been producing data at collision energies of 13.6 trillion electron volts, the highest ever achieved. The experiments have been collecting data and refining the precision of their measurements, accumulating the large datasets needed to confirm or rule out hints of new physics. In 2024 alone, the LHC delivered 124 inverse femtobarns of integrated luminosity to the ATLAS and CMS experiments, a measure of the total number of collision events recorded. And similar production was planned for 2025 before the accelerator enters a long shutdown in July 2026. That shutdown, Long Shutdown 3, will last until around 2030, and during that time the LHC will be substantially upgraded to become what is called the High Luminosity Large Hadron Collider, or HLLHAC. This upgraded machine will not run at higher energies, but it will produce collisions at a much higher rate, increasing the integrated luminosity by a factor of 10 compared to the original LHC design. Over its operational lifetime from 2030 to 2041, the HLLHC is expected to produce around 4,000 inverse femtobarns of data, compared to the 500 produced by the LHC in all of its running since 2010. That is an enormous increase in statistical power. Rare processes that have been seen only as hints will become established discoveries. New rare processes that have not yet been detected at all will become accessible. If the kaon anomaly and other deviations from the standard model are real, the HLLHC era will either confirm them definitively or demonstrate that they were statistical fluctuations. The HLLHC will produce roughly 380 million Higgs bosons during its operation, compared to the approximately 55 million produced by the LHC in all previous running. This enormous sample of Higgs bosons will allow physicists to study the Higgs particle with a precision that was previously unimaginable, measuring all of its properties with extraordinary accuracy and looking for any deviations from standard model predictions. Some theorists predict that subtle anomalies in Higgs physics, in the way it decays, in the strength of its interaction with other particles, might be the place where new physics first clearly reveals itself. Beyond the HLLHC, CERN and the global particle physics community are planning something even more ambitious, the Future Circular Collider, or FCC. This proposed machine would be housed in a new tunnel, approximately 91 kilometers in circumference, roughly 3.5 times the size of the LHC tunnel, bored deep underground on a route that would run from beneath the Swiss countryside and loop back under the Jura Mountains. A feasibility study for the FCC was completed and delivered to CERN in March 2025, finding the project technically and financially viable. If approved by CERN's member states in the late 2000s, construction could begin as early as 2030. The FCC would be built in 2 phases. The first phase, called FCCIEE, would be an electron-positron collider, a factory for producing enormous numbers of Higgs bosons, Z bosons, W bosons, and top quarks with extraordinary precision. Electrons and positrons are fundamental particles, unlike the composite protons used in the LHC, so their collisions are cleaner and easier to interpret, allowing much more precise measurements. The FCCEE would be the most powerful tool ever built for studying the Higgs boson in detail, and it would also be one of the most sensitive probes for anomalies in the behavior of the known particles. The kind of tiny deviations that might betray the presence of new physics, even if that physics is at energy scales too high to be directly produced. The second phase, FCC-HHH, would be a proton-proton collider operating at collision energies of 100 trillion electron volts, roughly 7 times the energy of the current LHC. At that energy, if new particles exist at masses accessible to such a machine, they would be produced directly and could be detected. The FCCHH would extend humanity's direct reach into the subatomic world by a factor of 7 beyond anything currently possible, exploring territory that is now completely dark to us. The total cost of the FCC project is estimated at many tens of billions of euros over its full lifetime, and its construction would mobilize the expertise of engineers, physicists, and technologists from around the world. It would represent the largest scientific undertaking in human history. Some physicists have argued that such an investment is justified by what is at stake, that understanding the fundamental nature of reality, including the resolution of dark matter, dark energy, the matter-antimatter asymmetry, and the incompleteness of the Standard Model, is worth any reasonable cost. Others have questioned whether the investment is justified, given the LHC's failure to find clear new physics so far, arguing that it might be more productive to invest in other approaches to fundamental questions. The debate will continue. But what is not in dispute is that the cracks in the Standard Model, the kaon anomaly, the muon magnetic moment, the matter-antimatter puzzles, the existence of dark matter and dark energy, all demand an answer. The universe has not finished speaking, and humanity has not finished listening. The Higgs boson and the weight of everything. Before we arrive at the closing of tonight's journey, let us linger for a while on perhaps the most celebrated discovery in the history of CERN, because understanding it makes the current anomalies so much richer. On the 4th of July, 2012, physicists gathered in a large auditorium at CERN, and in the audience sat an elderly Scottish man named Peter Higgs, who had proposed the existence of a particular particle back in 1964. When the spokesperson for the Atlas experiment took the microphone and confirmed that a new particle had been observed in their data, a particle consistent with the Higgs boson, Higgs wiped a tear from his eye. He had waited 48 years for that moment. The Higgs boson is special. It is the particle associated with the Higgs field, a quantum field that permeates all of space. Unlike the other force-carrying particles, the Higgs field is not associated with a force in the conventional sense. It does not push or pull objects together or apart. Instead, it does something far more intimate and fundamental. It gives other particles their mass. When particles move through the Higgs field, some of them interact with it strongly, and others interact with it weakly. The strength of that interaction determines how much mass a particle has. The electron interacts relatively weakly with the Higgs field, so it has a relatively small mass. The top quark interacts with it very strongly, which is why the top quark is the heaviest known fundamental particle, approximately 173 times heavier than a proton. Photons and gluons do not interact with the Higgs field at all, which is why they are massless and travel at the speed of light. Think of the Higgs field as a kind of cosmic molasses that fills all of space. Some particles move through it easily, barely feeling its presence, and those are the light particles. Others push through it with more difficulty, as though wading through thick liquid, and those are the heavy particles. The field is everywhere and always, inside your body, inside the atoms of the chair you are sitting in, inside the sun, in the space between galaxies. It has been permeating the universe since a fraction of a second after the Big Bang, when it settled into its current state in a process physicists call a phase transition, similar in some ways to water freezing into ice. Before that phase transition, all particles were massless and traveled at the speed of light. The universe was a very different place. The confirmation of the Higgs boson completed the Standard Model. It was the last piece of a puzzle that had been assembled over decades. And yet, ironically, discovering the Higgs boson has raised as many questions as it answered. The Higgs boson's mass itself is puzzling. According to the logic of quantum field theory, quantum fluctuations, the constant buzzing activity of the quantum vacuum, should drive the Higgs boson's mass up to an enormous value, far above what has been measured. The only way to get a Higgs boson as light as the one observed is if enormous positive and negative contributions from quantum corrections nearly perfectly cancel each other out, leaving a tiny residual value. This exquisite cancellation seems highly improbable without some deeper principle governing it. And that is precisely the hierarchy problem that supersymmetry and other beyond Standard Model theories are designed to solve. Moreover, the Higgs boson has subtle properties that can potentially reveal the presence of new physics. The way it couples to other particles, the strength of its interaction with each of the Standard Model particles, is precisely predicted by the theory. Any deviation from these predicted coupling strengths would be a clear sign of new physics. The HLLHC and the proposed FCC collider are both specifically designed to measure Higgs couplings with extraordinary precision, looking for exactly these deviations. Some theorists believe that the Higgs boson, precisely because it is the newest and least well-understood part of the Standard Model, is the most likely place where the theory's cracks will become most clearly visible. There is also the question of whether there is one Higgs boson or several. The Standard Model requires only one, but many extensions of the model predict multiple Higgs bosons, 2, 5, or even more, with different masses and properties. Finding a second Higgs boson would be as dramatic a discovery as finding the first. The LHC searches for heavier Higgs-like particles in every run, and while none has been found yet, the search is far from complete. And then there is the question of what the Higgs field is, at a fundamental level. Why does it exist? Why does it permeate all of space? Why does it have the particular strength of interaction with each particle that it does? These are deep questions that the Standard Model does not answer. It simply takes the Higgs field as a given, a feature of the theory rather than something explained by it. Whatever physics lies beyond the Standard Model must eventually explain the Higgs field's existence and properties from more fundamental principles. That is part of what makes the search for new physics so compelling. It is, in the end, a search for the explanation of why matter has mass, why objects have weight, why the universe is the way it is rather than some other way. Gravity's absence. The missing force. There is one profound absence in the Standard Model that deserves its own unhurried exploration, because it sits at the heart of why physicists know the theory must eventually be superseded. The Standard Model describes 3 of the 4 known fundamental forces of nature with extraordinary success. But the 4th force, gravity, is absent. The theory of gravity is general relativity, Einstein's masterwork, which describes the force of gravity as a consequence of the curvature of spacetime caused by the presence of mass and energy. General relativity is itself an extraordinarily successful theory, confirmed by observations ranging from the bending of starlight around the sun to the detection of gravitational waves from merging black holes a billion light-years away. But general relativity and the Standard Model cannot both be right in their current forms, and physicists have known this for decades. The problem arises when you try to apply quantum mechanical principles to gravity. When you try to build a quantum theory of gravity the way the Standard Model is a quantum theory of the other 3 forces. When physicists attempted this in the mid-20th century, the calculations exploded into meaningless infinities that could not be tamed by the mathematical techniques that worked for electromagnetism and the nuclear forces. The combination of quantum mechanics and general relativity appears to be internally inconsistent at the energy scales where both theories should simultaneously be important. Near the centers of black holes, at the very beginning of the universe, or at the scale of a quantity called the Planck length, which is about 10 to the power of minus 35 meters, 20 orders of magnitude smaller than a proton. This conflict between general relativity and quantum mechanics is one of the most important unsolved problems in theoretical physics. A complete theory of quantum gravity. 1. That correctly describes the gravitational force in quantum terms does not yet exist. String theory and loop quantum gravity are the 2 leading candidates, each with substantial mathematical development behind them, but neither yet making clear, testable predictions that experiments can decisively confirm or rule out. The graviton, the hypothetical particle that would carry the gravitational force in a quantum theory, just as the photon carries electromagnetism, has never been detected, and may not be detectable with any foreseeable technology. Gravity is incomparably weaker than the other forces at the subatomic scale. The gravitational attraction between 2 protons is roughly 10 to the power of 36 times weaker than the electromagnetic repulsion between them. Any experiment sensitive enough to detect a graviton would need to be so massive that it would collapse into a black hole before the measurements could be made. The graviton's existence is a theoretical necessity rather than an experimental reality. What this means in practice is that the Standard Model, however successful, is operating in a domain where gravity is completely irrelevant. The energies of particle physics collisions are far below the scales where quantum gravity affects matter. This is like having a complete theory of weather that works perfectly well at atmospheric scales, but says nothing about the nuclear reactions inside the sun that ultimately drive all weather systems. Useful within its domain, but clearly not the final word on nature. The dream of theoretical physics, the dream that has driven the search for grand unified theories and string theory, and all the other beyond Standard Model frameworks, is a single unified theory that describes all four forces and all matter within a single consistent mathematical framework. A theory of everything. Einstein spent the last 30 years of his life searching for it, without success. His successors have spent decades since then adding mathematical sophistication and physical insight to the search. And while beautiful structures have been built, the final theory remains elusive. Some physicists think we are close. Others think the goal might be fundamentally unattainable. Most keep searching. Every anomaly at CERN, every crack in the Standard Model, carries within it the hope that it might be a clue pointing toward unification. A new particle found at the LHC might be a supersymmetric partner, which would in turn provide evidence that string theory, the leading framework for quantum gravity, is on the right track. A deviation in kaon decay rates might point toward a new force, and new forces at low energies sometimes reveal their connection to quantum gravity at very high energies. The physics is connected in ways that are not always obvious from the outside. Every measurement matters. Every anomaly is worth taking seriously. The human story behind the science. Let yourself soften into this section now. The science is beautiful, but the story behind it is beautiful too. The story of the people who spend their lives in service of these questions, who wake before dawn to analyze data and stay late into the night checking calculations, who carry the weight of not knowing and find meaning in the search itself, rather than only in the arrival. CERN is, in its way, one of the most remarkable human institutions ever created. It was founded in 1954 in the aftermath of the Second World War as a deliberate act of reconstruction, not just of buildings and economies, but of something more fragile and more important. The idea that nations could work together toward a goal that transcended politics and nationalism. 12 European countries came together to build a laboratory dedicated entirely to fundamental science, to questions with no immediate practical application, to the deep human need to understand what the universe is made of. They agreed that science, at its most fundamental level, belongs to everyone. Today, CERN has 23 member states and dozens of associate and observer countries. The collaborations that operate the major LHC experiments, ATLAS, CMS, LHCb, ALICE. Each involve thousands of scientists from hundreds of institutions across more than 100 countries. The analysis of LHC data involves a global computing grid linking more than 100 data centers around the world, collectively managing more than an exabyte of stored data. An exabyte is 1 billion gigabytes, enough to fill roughly 30,000 years of continuous video recording. And all of it is being processed and analyzed by physicists from every continent on Earth, speaking dozens of languages, representing every conceivable cultural background, united by the simple agreement that the question matters more than the questioner. The NA62 experiment that produced the Kaon result is itself a collaboration of physicists from the universities of Lancaster, Birmingham, Bristol, and Glasgow in the United Kingdom, alongside colleagues from Italy, Switzerland, France, Russia, and many other countries. The spokesperson who presented the result in September 2024 was Giuseppe Ruggiero of the University of Florence. The lead data analyst was Joel Swallow. The physics coordinator was Karim Masri of Lancaster University. These are not famous names outside of physics. They are not household celebrities. They are people who spent years, in some cases more than a decade, working on a single experiment, driven by the conviction that finding one signal in 10 billion was worth the effort. There is something deeply admirable about that kind of commitment. We live in a world that often demands fast results, immediate impact, visible return on investment. Fundamental physics offers none of those things. The payoff is uncertain, possibly decades away, possibly never coming in, the form the researchers hoped. And yet the scientists persist. They persist because the questions are real and the universe is genuinely not yet understood, and someone has to do the work of trying to understand it. They persist because there is a particular kind of joy in being at the frontier, in working on problems where no one knows the answer yet, where every calculation might be the one that changes everything. Peter Higgs proposed the field and boson that bear his name in 1964 and lived to see their discovery in 2012. 48 years. That is a long time to wait for confirmation. He shared the Nobel Prize in Physics in 2013 with François Englert, who had independently developed related theoretical ideas. Both men were in their 80s by then. There is a lesson in that patience, in the willingness to do the intellectual work, to contribute to the accumulation of understanding without any guarantee of personal vindication within one's own lifetime. Consider also the story of neutrino physics, another area where anomalies eventually led to paradigm-shifting discoveries. For decades, experiments studying the neutrinos produced by nuclear reactions in the Sun measured far fewer of them reaching Earth than the solar models predicted, a discrepancy known as the solar neutrino problem. Some physicists suspected the solar models were wrong. Others suspected the neutrino detectors were malfunctioning. The real answer, which emerged only gradually over the 1990s and 2000s, was that neutrinos were oscillating, spontaneously changing from one type to another during their journey from the Sun to Earth. The electron neutrinos produced in the Sun were partially converting into muon neutrinos and tau neutrinos, which the original detectors could not detect. Neutrino oscillation required neutrinos to have mass, but the standard model predicted that neutrinos were massless. The confirmation of neutrino oscillations, which earned the 2015 Nobel Prize in Psi Physics for Arthur MacDonald and Takaaki Kajita, was the first direct experimental evidence that the standard model was incomplete. The anomaly had been pointing at new physics all along. The solar neutrino problem was recognized in the 1960s. Its resolution came in the early 2000s. That is roughly 40 years from anomaly to understanding. The current kaon anomaly was first measured with meaningful precision in the mid-2000s. If history is a guide, the patience required to understand it fully might be measured in decades. That is the pace of fundamental physics. It is not a pace well suited to the rhythms of modern life, with its demand for immediate results and constant novelty. But it is the honest pace of inquiry into questions that have never been answered before. The physicists working today on the anomalies in kaon decay, on the muon magnetic moment, on the matter-antimatter asymmetry in baryons, they may be in the same position Higgs was in during the long decades between his theoretical proposal and its experimental confirmation. They may be working now on measurements that will be understood only years or decades hence, when the full picture has assembled itself, and it becomes clear that this particular measurement, made in this particular year, was the first glimpse of something fundamental. Or they may not. Science is honest about that uncertainty. Not every anomaly reveals new physics. Not every measurement that deviates from predictions is pointing to something real beyond statistical noise. But you have to take them seriously. you have to look, because the ones that are real will not announce themselves loudly. They arrive as whispers, as small discrepancies, as barely there shifts in a number, and the scientists who notice them and investigate them and resist the temptation to dismiss them are the ones who open the next chapter of understanding, closing. We have traveled a long way tonight, from the cool underground tunnels of CERN to the boundaries of the observable universe, from the quarks inside a proton to the dark energy that fills all of space, from the triumph of the Standard Model to the tantalizingly imperfect measurements that suggest it may not be the last word. Let all of that settle around you now like the air of a quiet room, gentle and present, and completely unhurried. There is something I want to leave you with as you drift toward sleep, something worth carrying with you into the quiet darkness of rest. It is this: the fact that we do not fully understand the universe is not a failure of science. It is science's greatest achievement. Because 100 years ago, we did not know that the universe was expanding. 200 years ago, we did not know that atoms existed. 300 years ago, we did not know why the planets moved as they do. At every stage in the history of human inquiry, there has been a frontier, a place where knowledge ends and mystery begins. And at every stage, the people at that frontier have been doing the most extraordinary thing that human beings do: asking, carefully and honestly and persistently, what is really there. The crack in the Standard Model that CERN's measurements are revealing is not a broken wall. It is a door. Somewhere on the other side of that door is a more complete picture of what reality is made of, one that will, inevitably, answer some of our current questions and raise new ones we cannot yet imagine. That is the nature of knowledge. It deepens infinitely. The universe has been unfolding for 13.8 billion years, and it shows no signs of running out of secrets. Consider for a moment the strange, layered beauty of what we have explored tonight. That inside every atom in your body, inside every carbon atom and hydrogen atom and oxygen atom that makes you what you are, there are protons and neutrons. And inside those protons and neutrons there are quarks, bound by gluons in a constant frenzied dance that has been going on since the first fraction of a second after the Big Bang. And those quarks are subject to forces: the strong force, the weak force, electromagnetism, that are described by the equations of the Standard Model with a precision that is, quite genuinely, astonishing. And yet those same equations leave more than 90% of the universe completely unexplained. The atoms you are made of are the exception. The majority of the universe is dark and unknown and waiting. And somewhere in Switzerland, 100 meters underground, protons are racing around a cold ring at 99.9999991% of the speed of light, waiting to be steered into each other. In a few years, after the HLL-HC upgrades are complete, they will collide more frequently than ever before, generating more data than any previous generation of physicists could have imagined. Somewhere in that data, perhaps hidden in the masses of collision events, perhaps in the rare decays of beauty quarks or kaons, perhaps in the subtle properties of the Higgs boson, the universe may be preparing another whisper, another small discrepancy, another tiny deviation from the predictions of the theory, nudging it slightly away from perfect match with reality. When that happens, if that happens, the physicists will look at their screens, at the numbers, at the histograms where reality has drawn a line that does not quite follow the curve the Standard Model drew first. and they will check their work, and they will check it again. And gradually, carefully, after many checks and challenges and independent confirmations, they will allow themselves to believe that the universe is telling them something new, that there is more to existence than the current framework describes. And the world of physics will shift quietly at first and then all at once toward the next question. That is how it has always worked. That is how it will always work. The universe is not finished speaking, and humanity is not finished listening. The questions that seem most unanswerable today: what is dark matter? Why is there matter rather than antimatter? Why does gravity refuse to fit into the quantum framework? What was the universe like in the first trillionth of a second of its existence? These are not permanent mysteries. They are temporary mysteries, held in place only by the limits of our current instruments and theories. Each generation of physicists inherits a more powerful set of tools and a deeper set of questions, and each generation moves the frontier a little further. The kaon that decayed in a CERN detector, producing a signal 50% higher than the standard model predicted, did not know it was doing something important. The particle did what particles do. It obeyed the laws of nature. The laws just turned out to be slightly different from what the equations said. And that tiny, infinitesimal discrepancy, that barely there whisper from the quantum realm, may be the first word of a new chapter in the story of what everything is. Breathe slowly now. Feel the weight of your body exactly where you are. Notice the rise and fall of your chest, the quiet rhythm of your own existence. Billions of atoms in precise, intricate relationship with each other, governed by the same laws that govern the stars, subject to the same forces that bind quarks inside protons and drive galaxies apart across the expanding universe. You are, in a very real and literal sense, made of stardust, of atoms forged in the hearts of stars that lived and died billions of years before our sun was born. The carbon in your body was produced in stellar fusion. The iron in your blood was created in supernova explosions that scattered heavy elements across the galaxy. You are a temporary arrangement of some of the oldest material in the universe, briefly organized into a form that can wonder about its own origins. That is an extraordinary thing. And the fact that you are spending some of tonight thinking about it, about CERN and Kaons and the crack in the fabric of what we know, means that the universe is, through you, looking at itself and asking questions. That is what consciousness does at its best. It turns the universe's attention back on itself, with curiosity and care and the willingness to revise what it thinks it knows. Think of that as you settle into sleep. Somewhere underground, the instruments are still running. The data is still being collected. The protons are still racing around their great cold ring at nearly the speed of light, 11,000 times per second, waiting for the moment when the next collision produces something no one has ever seen before. The physicists are still at their desks and their screens, still turning the numbers over in their minds, still checking their work, still asking the question that has no final answer, and never will. What is this place, this universe, and what are we made of? That question, and the people who spend their lives asking it, are among the most beautiful things our species has produced. Rest in that thought now. Let your breathing slow. Let the equations and the particles and the tunnels and the detectors all drift together into the peaceful quiet of sleep. The universe will still be here when you wake up, full of mystery and light, full of questions not yet asked and answers not yet found. And somewhere a detector is recording data, and somewhere a physicist is looking at a number that does not quite fit, and somewhere the next discovery is already waiting in the data. If this journey resonated with you tonight, if the science and the wonder stayed with you in that comfortable space between waking and dreaming, please do hit the like button and subscribe to the Science Pillow. Your support keeps these late-night journeys possible, and every subscription genuinely means the world to this channel. Sleep well, and I will be here when you return.